All right, we have just a few more to finish here on the Lewis structure and polarity video guide. This is going to be part 2. And so we're going to start out here with silicon dioxide. Okay, so once again, silicon happens to have 4 valence electrons. Things that have 4 love to be in the middle. Okay, so we're going to put our 4 valence electrons here. Okay, oxygen has 6 each, so when I go to draw it, I'm going to put oxygen and I'm going to draw the 6 in a particular way. I'm going to do this kind of in a rotation. And put 1 here, 1 here. Okay, so each oxygen has 6. Okay, you probably can recognize they're going to share more than one pair. We're going to have some multiple bonds here. Okay, and so if you look at this, when you go to draw this, here's silicon in the middle, double bond to this oxygen with its 2 lone pair. We're going to do the same thing for this oxygen, double bond, okay, couple with its lone pair. This is kind of how it has to be, where everything ends up with its octet. We have the right number of valence electrons. Okay, so if I want to compare the electronegativity difference, you're going to see oxygen has an electronegativity of 3.5. And what's silicon? 1.8. So if I compare those electronegativities, the difference is 1.7, which gives this thing polar bonds. Okay, well, let's look at the geometry for this thing. Okay, around the central atom, remember double bonds count as 1 effective pair. 1, 2 effective pairs. There are no lone pairs around this thing. I use my diagram, 2 effective pairs with 1 lone. This thing is linear, it's a line. Okay, let's look at our model, see if we can construct that. Okay, so we had 2 double bonds, no lone pairs around this thing, definitely linear. And if you look at it, no matter how you arrange this thing, notice how they line up. And so think about this. Oxygen is way more electronegative. This oxygen atom is pulling the electrons this way. This oxygen atom is pulling the electrons this way. They're equal and they're opposite. And so it's kind of like that tug of war with equal strengths on each side. Okay, since they're equal, they cancel. So even though this has polar bonds, there isn't going to be a positive and negative region because the 2 strengths, the 2 poles, are pulling 180 degrees apart from one another. They're perfectly symmetrical. This is going to be a non-polar molecule. And because, once again, symmetry is playing a role. Okay, next one, we have oxygen, okay, just diatomic oxygen. Well, first off, let's draw this. Okay, we're going to draw this one with 6. I'm going to draw another one over here and give it 6. I think you can recognize it's going to have to share more than 1 pair, so it's going to end up looking like this. We don't have to look up the shape because, once again, there are only 2 atoms here. Between any 2 points, there is a straight line. This is linear. Okay? And then we really don't even have to look up the electronegativity, even though we know it's 3.5. Well, anytime you subtract a number from itself, you get 0.0. This is nonpolar. And that makes sense because why would the electrons prefer one of the oxygen atoms over the other? They're going to share equally. They have equal strength. There's no additional attraction. This is a nonpolar molecule. Okay, and then last but not least, we got one more. So carbon tetrachloride. Let's take a look at this one. Carbon's going to be in the center. Loves being in the middle with its 4 valence. Okay, and I think you can recognize the chlorine's going to go like this. I didn't make my marker thinner. I'll do that here in a second. Okay, and then I'll just draw it. Make this thinner. Okay, carbon's going to go in the middle. And you can draw it like this. We've seen this shape before. Okay, in the center, we have 4 effective pairs with no lone. This is a tetrahedron. Tetrahedral. If you want to draw it kind of more 3-dimensionally, you can do it in this fashion. where I'm going to put these three in the same plane. I can demonstrate this one's kind of popping out and this one's kind of going away from you. That's a way you can kind of draw a tetrahedral shape in 3 dimensions. I can share that with you on here. Let's remove these. Let's just put 4 on that central atom. Once again, there's that tetrahedron shape, right? Kind of like a pyramid with something sticking out of the top. Okay, that is a tetrahedron, perfectly symmetrical. And so, if I want to compare these bonds, let's see. Chlorine has an electronegativity of 3, and carbon has an electronegativity of 2.5, which gives me 0.5, which tells me I have polar bonds. However, because it is perfectly symmetrical, tetrahedron, perfectly symmetrical, those polarities cancel out. So this is going to be a non-polar molecule. So hopefully, going through some of those, you kind of got a better feeling for how to draw Lewis structures, how to determine if bonds are polar, nonpolar, or ionic, and then looking at the geometry. Is the geometry, are the atoms configured in such a way that they're the pull of the more electronegative element, do they cancel each other out? Are they equal and opposite? So there are some additional practice problems, and thanks for watching.